Welcome back, DeepVisus Explorers, to Where Vision Meets Depth. Today, we delve into a fascinating new paradigm for artificial intelligence inspired by how we understand and create. In this episode, our journey is guided by the work titled Regeneration Learning, a learning paradigm for data generation, published by Su Tan, Tao Qin, Jiang Bian, Taiyan Liu, and Yoshua Bengio at the 38th AAAI Conference on Artificial Intelligence, also known as AAAI 24. The core problem this paper addresses is a fundamental challenge in machine learning, generating complex, high-dimensional data, like images or video, from a simple input. This process is often hindered by what the authors call a one-to-many mapping problem. Think about it. A single word like dog can correspond to countless different images of dogs. How do we teach an AI to handle this vast complexity without getting overwhelmed? This leads us to our central question. How can we simplify the challenging task of data generation to make it more efficient and effective? The authors propose a new learning paradigm called regeneration learning to tackle this very problem. The key insight is to break down the complex, one-step process of generating data into a simpler, two-step process. Instead of a model directly generating the final, complex data, which they call Y, from the initial source data, which they call X, regeneration learning introduces an intermediate step. First, the model generates an abstract or representative version of the target data, which they call Y', from the source data X. This Y' is a simplified, more compact version of the final output Y. For example, in a text-to-speech task, the source data X would be the text, and the final target data Y would be the speech waveform. The intermediate representation, Y', could be a spectrogram of the speech. This conversion from the complex Y to the simpler Y' can be done with explicit transformations, like a Fourier transform, or implicit ones, using models like a variational autoencoder, or VAE. After this first step, the second step is to generate the final, complex target data Y from the intermediate representation Y'. Because Y' is a more compact representation of Y, the mapping from X to Y' is less complex and has less of the one-to-many mapping problem than the direct mapping from X to Y. The process of generating Y from Y' can be learned in a self-supervised way, using large amounts of unpaired data Y. This makes the whole process much more data efficient. The authors draw a powerful analogy between regeneration learning and a more traditional machine learning concept, representation learning. In representation learning, which is typically used for tasks where we are trying to understand data, such as image classification, the goal is to create a compact representation of the source data X, which they call X'. This makes the task of classifying X' into a target label Y much simpler. Regeneration learning, on the other hand, is the counterpart for data generation tasks. Instead of simplifying the source data, it simplifies the target data. This new paradigm can be applied to a wide range of tasks, including text generation, speech recognition, music composition, and image generation. So, what are the main takeaways? Regeneration learning offers a powerful solution for conditional data generation tasks by breaking down a difficult problem into two more manageable steps. It is particularly useful in situations where the target data is high-dimensional and complex, or when there is a significant information mismatch between the source and target data. By creating an intermediate, abstract representation, it simplifies the generation process and can even be trained more efficiently using self-supervised learning techniques. To answer our central question, how can we simplify the challenging task of data generation to make it more efficient and effective? The paper's answer is clear: by not attempting to generate the final data all at once. Instead, we first regenerate a simplified version of the target data, and then, in a separate step, generate the final complex data from this simplified representation. As we close this chapter, remember that the quest for true intelligence, whether biological or artificial, is an unending symphony of discovery. Join us next time on DeepVisus as we tune into another frequency of the brain, mind, and intelligence, unraveling the mysteries that shape our understanding of thought itself.